So we've seen about computation. Okay, we've talked about computation and with the shell before. So yeah, we've seen that computation occurs in nature at some point. It's clear, and especially with DNA. And okay, but we also want to describe the complexity of something independently of whether it's computation or not. Okay, we would like to be able to describe the complexity of a fractal, or to tell that it's difficult or it's complex or not. And we may use some kind of concept, some of the concepts that were used in computer science to do so. So basically, so you might not agree with that, okay? But I have arguments. So the first thing is that everything that will ever be said, okay, that will ever be written, that will ever be executed, or will be a finite sequence over a finite alphabet. Okay, if you consider an article in biology or whatsoever, okay, it will be a sequence of 0 and 1s. It will be a PDF file, and it's a sequence of 0 and 1s. Okay. Differential equations do not exist in computers. Okay? Computers compute on finite numbers. The floating point precision is limited. Everything. So everything is discrete. I mean, everything is integers at the end. Okay, it's a series of zeros and ones. Okay, so even if you may consider that your precision can be arbitrarily large, it will still remain an integer. Okay, it will be a larger integer, but still an integer. Okay. So once this said, okay, that's basically you can look at everything like as a word on 0 and 1s, at least theoretically. Okay, but concretely as well, because PDF file is a PDF file, it's 0 and 1s. Okay, nothing else. Okay. So what can we do with that? How can we say that something is complex? Okay. So I would like to tell more than it looks complex. Okay. Or we don't know. Okay. So one way, once we have computers, one way to think about it is just to say, okay, maybe something complex is something that takes time to do it. Okay, or requires a lot of knowledge. Okay, you cannot guess what's going on. Okay, you need to know a lot on the object in order to build it. Okay, if you need few things to build it, then it cannot be very complex. Okay, with a small small guide, you will be able to construct it. Okay, the things that are really complex is the one that requires a huge book to build it. Okay, if you just require a small set of information, then it might not be too complex. Okay, so that's basically the idea of Solomonov, Kolmogorov, and Chaitin in '66. Is that let's try to define the complexity of an object as the size of the smallest program that generates it. Okay, so remember that we have a universal Turing machine, okay, that can execute any program on any input. Okay, so you just take an arbitrary universal machine. Okay, it doesn't really matter in the sense that I will define later on. Okay, so you take one universal Turing machine. Okay, and you ask the question, what is the smallest program that if I execute it on the Turing machine, universal Turing machine, then I will get the sequence I'm looking for. Okay? So you're looking for the shortest program that will generate your picture or whatsoever. Okay? And let's call it the complexity of your object. Okay? This is quite a reasonable thing. Okay? So for instance, the complexity, the k complexity of this sequence of bit, okay, 0, 1, 1, 1, 0, 1, okay, you can say that it's at most 8, because I have here a program that writes this thing, which is just print the sequence. Okay, and the sequence has length 7. So basically, here I have a program of length 8 that prints the sequence. So I know that this complexity is less than 8. Okay. More. So basically, what can we say about it? Is that it's a fairly nice definition. In the sense that it really captures some things. That means that it really captures what's particular about this sequence, and as opposed to others. Okay, it really captures here what I have to put in the program is what is really specific to the sequence. The things that are not specific to that sequence, I can just use the universal Turing machine to do it. Okay, so this really measures something. And it turns out that clearly it's related to compression. Okay, clearly what it does here is just trying to compress the sequence. Okay, and look at the size of the compressed files. Okay, so what you know is that first that everything cannot be small. Cannot have a lot of things have to have a high complexity. Why? Because simply you have a finite set. Okay, so if you consider all the sequence of length n, okay, there are 2 to the n of n of it. Okay, and you want to find the smallest program that can generate all these things. For each of them, you want to find the smallest program. So if for all of them the program was of length n-1 for all of them, then you would have a problem because you would have only 2 to the n-1 program, and this could generate only half of them, not all of them. Okay, so you know that there is at least a huge part of, at least half of it, have maximum complexity. Okay, so there are a huge number of strings that you won't be able to compress in any way. Okay, so you have a huge number of things that are very, very complex in that sense. Okay, but what you know is that you can always write print followed by the sequence, so you know that the complexity is at least, at most, the length of the string, more or less. Okay? So, interesting things is that if you look at the strings with highest complexity, as we've seen here, the one that have complexity at least n, okay, then it turns out that they have pretty much the same, they have exactly the same statistical properties as random strings. What do I mean by that? I'm not so sure. It's basically that you cannot write a program that will be able to distinguish between them and random sequences, more or less. It's basically the idea. But there is a theorem there, but I'm unable to write it, okay, to tell it exactly. But basically what you have here is that given this measure of complexity, you have, if you look at the complexity scale, with the Kolmogorov complexity, basically what you have below is that things that requires a very small program to compute. Okay, so you have easy things, not complex. Okay, you have things that are not complex. Okay, and all above you have random strings. Okay, the one that are the most complex is randoms. So, do you agree that random things are complex?
In that definition, yes. Generally speaking, absolutely not.
Why?
Because you can write a program that very simple that generate a random sequence. It's not the one that you want.
Exactly. That's the issue. That's the problem. Okay. So this might appear shocking, but random stuff is hard. Okay, that might be shocking because, you know, random is just random. Who cares? It's just noise. It's no problem. But that's exactly the issue. Is that noisy stuff, okay, it's unpredictable in some sense because it's arbitrary. It's completely random. So there is a huge difference between describing the set of things, so the random strings,